Hi, it's time for another math easy solution. Today I'm going to go over further into the vectors and the geometry of space video series, and now look at the review, which is at the end of this chapter in my calculus book. Alright, and before we get further, as always, if you don't have time to watch the whole video, you can play this video at a faster speed. And top secret life hack, your brain gets used to faster speed. And there's a link to the tutorial I have over there. And also you can download and read the notes. I'll link the link to the PDF notes will be in the description below, as well as the notes on the Hive blockchain and article format. And also you could watch a video in parts. All the timestamps of all parts are in the description. And also I should be making a video sections playlist on this if they're not too short each question. But I will make some of them on there, which is just basically shortened clips taken from this long video, and post those separately. Anyways, and let's continue further. So here's calculus book reference. Note that I mainly follow along the following calculus book. This is Calculus Early Transcendental 7th edition by James Stewart. And note, in the earlier videos I used the 6th edition. Alright, now the next section is, sections in calculus book chapter. So I've made a list of the sections in this particular chapter with links to the Hive posts of the videos I have already finished. Note that I've started splitting each long video into sections and made a playlist for each. So here's a link to the playlist right here, Vectors in the Geometry of Space. Here's the 3D coordinate systems. Put a link to the Hive notes, and then there's a playlist link there for the sections. And then there's vectors and so on. And then we did all these ones, and the last one was the cylinders and quadric surfaces. And now the current one is review, and this is the links to them, which I'll be working on right now as a current video. Afterwards, we're going to do true and false quiz and problems plus in future videos, so make sure to stay tuned for those. Alright, so the next section is the topics to cover. Note that the timestamps will be included in the video description for each topic listed below. And I put these here just because I'm going to copy and paste and put the timestamps. So we're going to have a review, concept check, 19 questions. And there's questions 1 all the way to 19. So yeah, some of them are quick and some a bit longer, but they're pretty epic stuff. So let's just continue further. So review, concept check. So here's all 19 questions. I put them all here in case you want to either pause the video or download the notes and look at them yourself and try to solve them yourself. Yes, you can try to solve them yourself. And here's just scrolling it so you can see them all. And you can pause video and so on, and read them and try to solve them and see how well you did. Because I'm gonna go over the solutions right now. So there's question 1: what is the difference between a vector and a scalar? So let's just look at that right here. So basically copy and paste, and then I do the solution here. So going further, so question 1: what is the difference between a vector and a scalar? Alright, so solution: a vector is a quantity that has both a magnitude and a direction. For example, velocity. Yeah, for example, velocity is going in this direction. So you have, let's say you're going 50 miles an hour. So you're going 50 miles an hour and there's a direction there. And then a scalar, difference between that is it only has a magnitude. A scalar is a quantity that only has a magnitude. For example, temperature. Yeah, so temperature, if you have 50 degrees Fahrenheit or Celsius, it's you're just going to say that quantity, it's there's no direction in it. It just states that quantity, that's temperature of the room or whatnot. All right, so let's continue to question 2. So how do you add two vectors geometrically? And then also we're asked, how do you add them algebraically? So geometrically, so here's the solution. So we can add two vectors geometrically using the triangle or parallelogram law. And here what I've done is I just copied and pasted from my calculus book, because again, this is just a review on it. I can go into these in depth, so that's why you have to make sure to watch my earlier videos, all in the links here. So all these, this whole chapter, you can watch those and where I break them down slowly. But here I'm going to basically almost rapid fire through these, just to, again, it's a concept check, and to review that we're understanding this all probably. So how do you add two vectors geometrically? We can add two vectors geometrically using the triangle or parallelogram law. So if you have a vector like this, so u plus v, so you would take v, put it at the end or at the tail, at the head of this arrow there for u, and then draw u plus v there. So that's a triangle law. What you could also do is, let's say you could also go u like this, and then v like this, and then you can combine, and then you can move this v over to this side, like that, and then u on this other side. You basically draw a parallelogram where these are parallel. Yeah, so these are parallel, and then you can draw this u plus v or v plus u, and it's the same thing there. And we can add two vectors algebraically by adding their components. So if you know the coordinates of them, or the components of vectors A and B, so if you have the vectors A's coordinates A1 and A2, and B is B1, B2, then you can just add each ones individually. So A1 plus B1, A2 plus B2. So B2, yeah, this one like that. So that's how you can add them up like that. And we can visualize the geometric and algebraic vectors, vector additions at the same time. So here's a graph showing both of them. So here's A, and then you could put B on top of there. So you're adding these together. So you would put the B vector at the end. So the tail of the B connects to the head of the A. And then you could also put that in coordinate form. So the coordinates of this A is going to be a A1, and then A2, like that. A bit messy. But anyway, that's this A1x, and then the Y is A2, and here you can see the visually. So there's A2, B2, that's the Y component of it, like that. And then the X component A1, B1, like that. Just epic stuff there. All right, let's continue further. So question 3, if A is a vector and C is a scalar, how is CA related to A geometrically? And how do you find CA algebraically? So geometrically, CA shortens or extends A. Yeah, so if you have a vector A like this, with components A1, A2, so the X and Y, C, multiplying by a scalar, just multiplies all the components as well. This goes up, and then basically it's just exactly the same thing here, but scaled up. This angle is exact same. But this is going to be CA1, CA2. So everything's just scaled up and basically stretches it. So, and if you have a smaller number C, less than 1, it will shrink it. If you have a negative, it goes opposite. All right, and we can find CA by multiplying the components of the vectors A by scalar C. So if A equals A1, A2, and B equals B1, B2, then you have, and also this was actually added earlier. Yeah, this was added earlier for the addition right here, but you could also do the same thing with subtractions. A minus B vectors, you can subtract the components, and then C is scalar times by A vector, you just multiply the components, and same thing in 3 dimensions. So in similarly for 3-dimensional vectors, so A1, A2, A3 plus B1, B2, B3, again, you add the components, and you can subtract the components, and you can multiply with a scalar into each component. All right, so again, that's pretty epic stuff there, so pretty simple. And let's continue further to question 4. And this one states, how do you find the vector from one point to another? All right, and what this question is actually asking, and if we look at the solution, they're also asking for the position vector. What this means is, well, we could, first of all, we can subtract the components of the initial point to the terminal point of these vectors. If you have vector A and B, and then the vector from one point to another. So if you have 2 points like this, yeah, these are points, not vectors. So if you have 2 points, the vector between them is just a difference between them. So for example, the components here is x1, y1, z1. This is x2, y2, z2. So then the vector with components is the difference. So you subtract this one, x2 minus x1, y2 minus y1, z2 minus z1. You get this setup right here. And what you end up having is a position vector that starts from the origin in terms of its exact components, but it's parallel to this vector between the 2 points. So if you have a vector right here, this is representations of the vector A with A1, A2, A3. So if you have point A like this, capital A with point X, Y, Z, I mean, this is a point like that. Then B point is X plus A1, Y plus A2, and then Z plus A3. Then the difference is, well, you're just going to subtract these two right here. You're going to subtract this from this, so in other words, these all cancel out, and this cancels out, Z cancels out. You're just left with this right here, A1, A2, A3, and these are just parallel. So that's this is called the position vector of P, and that's the vector from one point to another. All right. So question 5: how do you find the dot product A dot B of 2 vectors if you know their lengths and the angle between them? What if you know their components? Again, these are just basically applying the equations that we covered in my earlier videos. So if you know the length of the vectors A and B as well as the angle between them, then we can find the dot product by the following formula, and this formula right here. So if theta is the angle between the vectors A and B, then A dot B is equal to the length, this is the length of the vector A, times by the length of the vector B, times cosine theta, and you get a scalar right here. It's often called a scalar product, I believe. All right, make this smaller right here. And this angle is the angle between the two vectors. So vector A and B, like that. So vector A and B separate like that. And also this vector can be considered A minus B. And the reason for this is if you add these two vectors together, so B plus this one right here, A minus B, you get this cancels out, you're just left with A. So that's just the vector A there. These are vectors. Like that. So that's epic stuff there. And yeah, so if we know the lengths and the angle, so if you know the lengths, and the angle between them, you just use this formula. And then if we know the components, we could just use a definition. So if we know the components of A and B vectors, then the dot product A dot B is given by the definition, which is the multiplication of corresponding components and adding them all together. So the definition of dot product, if A is components A1, A2, A3, and B as components B1, B2, B3, then dot product of A, B is the number A dot B given by, and you would multiply this one, and then add it to the multiplication of the middle one, and this one, and then the third one. So A1, B1 times, plus A2, B2, plus A3, B3. All right, and then question 6, we're asked, how are dot products useful? And so dot products, if you look at the solutions, dot products have many useful properties. One of them here, actually use ChatGPT for this. Calculus book didn't specify exactly all the useful cases, but anyways, they did a lot of them. They just didn't state them directly. So the number one property is determining the angle between two vectors. So if theta is the angle between the non-zero vectors A and B, then cosine theta is equal to A dot B, is the dot product, divided by the lengths. So you can determine this angle right there, cosine theta, and you can take the inverse cosine to get the angle. And all you need to know is the dot product and the length, and you can get the angle between them. So that's very, very, very useful. And again, I'm just using the same screenshots as before for this question. So if you know these vectors and a dot product, you can solve the dot product and the lengths. You know the lengths of them. This is the length right there. If you know the length, you can get the angle just by using a dot product, which is actually quite amazing. And then the second property is checks orthogonality, or in other words, if its vectors are perpendicular. So two vectors are orthogonal or perpendicular if their dot product is 0. And here what I just added quickly is also here, so two vectors are orthogonal or perpendicular if their dot product is 0, aka cosine 90 degrees is equal to 0. And you could see from over here, so cosine right here, theta. So if theta is 90 degrees, that's going to be, well, if you recall how it looks like, this is the graph of cosine. Looks like that. So this is at 90 degrees. So it's at 0. Yeah, so basically at 90 degrees or pi over 2, this is 0 is cosine. Yeah, cosine theta, like that. So that means then this is 0. The only way it's 0 if A and B, assuming they're not 0, they're not going to be 0, otherwise you'll be dividing by 0. So assuming the lengths aren't 0, the vectors actually have a size, these dot products are going to be equal to 0. So then that's going to be for perpendicular vectors. So two vectors A and B are orthogonal if and only if the dot product is equal to 0, A dot B is equal to 0. And also we could tell that if A dot B is greater than 0, theta is going to be acute. And if A dot B is equal to 0, or pi is equal to pi over 2, or 90 degrees. This is in radians, or pi over 2 radians, or 90 degrees. And if A dot B is less than 0, then the angle is going to be obtuse. And we can see this, again, as based on the cosine. So remember the cosine, it looks like that. And this is going to be, this is positive, is between 0 and 90 degrees, or pi over 2. Like that. And then it goes negative after that. So in other words, this angle, when the angle is small, you get A dot B has to be positive, because cosine is positive. And then when it's past 90 degrees, it's going to be obtuse. In other words, it's beyond angles bigger than 90 degrees. And another useful property is projecting one vector onto another. So recall scalar projection of B onto A. This would be the component of the vector B is equal to the dot product A dot B divided by the length A. So again, recall from earlier videos on that. And also vector projection of B onto A. This was the scalar, and now you could do the vector projection. It's going to be the same thing as this, but then you multiply by the vector divided by its length, so it's just a unit vector. like that. So you multiply top and bottom so that you can have the direction and it doesn't change the actual magnitude of the vector size. Like that. So projection of B is going to be, so vector projection, this is a scalar projection. So same thing there, component, and then multiplied by A times B. And you're going to simplify this, you're going to A dot B dot A divided by length squared. Like that. And here are some illustrations of these vector projections, again using dot product like that. So if you have vector A, vector B, and the projection of B onto A, scalar, and then the scalar formula is again using this one, and the vector is, if you get an actual direction, not just magnitude, you're going to get it over like this formula. And again, this is the vector projection of B onto A like this. And this is also the absolute, this is the length of this. You're also using the cosine. And it's the cosine theta there, where cosine number is adjacent over hypotenuse. Yeah, so if you have the length B like this length B, this right here is going to be the angle. This is, let's call this xy. So cosine theta is equal to x over absolute value of B. That's the adjacent over hypotenuse. So move this over, you're going to get this absolute value. You're going to get this length B times cosine theta is equal to the x component, or the vector projection of B onto A. All right, and there's the this is projection of A onto B. Just you draw the vector with a direction. This one is an actual length. All right, and also here you can also go in reverse direction as well. If the B angle is on the opposite of this one, it's going to be the same thing but negative, like that. So that's vector projections. Pretty epic stuff there. All right, and another property of dot products is calculating work done by a constant force. So if you have a force like here pointing theta from this direction right here of the distance. So if you have a force pulling something like this along this direction, but the force is pushing upwards at an angle, then you could take the projection of the force onto the distance vector, and you're going to get the work done. So when you multiply together, so work equals to this component of force, the absolute value of the length of the force, the magnitude of the force, times by the cosine theta, times by the distance. That's work as definition is just force times distance. And so, but since this force is at an angle, so you would take the component that's along this times by distance, and you get the formula for work. And then rearrange these together. It's going to be work equals F. Move this over. Absolute value of F times, just the length of force magnitude times distance magnitude times cosine. That's just a dot product. So in other words, when you have a force at an angle relative to the distance, the dot product is the work done. So an example of that is just a wagon. So if you have a wagon like here, and you're pulling it here at a distance in this direction, the dot product, if you know the length, if you know the force, you know the length. If you push this, let's say 50 newtons at that angle, and then this one right here, you're going to push this along this distance at 1 meter distance. So the force is going to be the dot product of that. So that's going to be the component of this along this side and there. And again, you could just use dot product, or you could use cosine and whatnot. Dot product, you just need the components and coordinates and so on. So these properties are very useful in many applications such as physics, machine learning. Dot product is fundamental in neural networks in measuring similarity between vectors, computer graphics, and engineering. And here's pause video and add to this note. So this was taken from ChatGPT. There's a link to it, and go read it there and so on. It's pretty useful. Pretty useful tool using AI and so on. So anyways, going further, so question 7. I think we got the right question. This was question 6. Yeah, so now let's look at question 7. Question 7 states, write expressions for the scalar and vector projections of B onto A illustrated with diagrams. Well, we already solved those in the useful properties of dot products. So what do you have those? The scalar and vector projections of B onto A are shown below, and here's a scalar projection of B onto A. Component of B onto A, that's the way you write it. So B onto A is equal to A dot B divided by the length A. And then the vector projection of B onto A is noted as projection of B onto A is equal to the component of B onto A. That's this part right here. and then times by this unit vector or whatnot, so whatever you like call it. Basically, yeah, unit vector in the direction of a. So a vector divided by the length a, and then equals to a dot b divided by the length a squared times by a vector, like that. And then the projections are seen visually below, like here. Yeah, so there's the vector projection. There's a scalar projection. You have b onto a, and you get the cosine of the length b. That's going to be this component b onto a. That's how you would term it, or how you would call it. And there's a vector projection. It's just without the cosine. It's just the direction. You don't need to know the magnitude. It's just going to be completely on it. So yeah, it does have magnitude and direction, but this is the projection. You have the direction of it. So the vector direction. So this is a projection of b onto a, and here's projection of b onto a if it's going on the negative side. If you have b pointing to the top left there. All right, going further. So question 8: how do you find the cross product a cross b of two vectors if you know their lengths and the angle between them? And then we're asked, what if you know their components? Yeah, so if you know their components, how do you get the cross product? This one is if you know their lengths and the angle between them, similar to dot product. So if we know the angle, let's look at the solutions. If we know the angle and the lengths of two vectors, we can determine their cross product via the following equation. That's this right here. If theta is the angle between A and B, so that theta is less than or equal to pi, and is greater than or equal to 0, like that. Yeah, then the length of A cross B is equal to the length A of the vector A times by length B, and then sine theta as opposed to cosine theta. Yeah, so sine theta, like that. Yeah, so this is the sine, but notice that this is the length of the cross product, and to get the direction of it, note that the right-hand rule gives the direction of the cross product and angle. Yeah, so if you have the vectors A and B like this, so if it's A there and B there, so A cross B is the angles can be determined from A to B like that, and the direction is going to be perpendicular using the right-hand rule where this curves in from where the angle is. So that's the angle curving in like this with your fingers, and then the thumb gives the direction of it. So all we could do is to say that it's this length of this. So we can determine the actual length using the using this formula like that, and then then we can just specify that the direction is going to be using the right hand rule. It's going to be perpendicular to A and B. So that's pretty much what we can give there. Yeah. So here I'll just clarify this. So if we know the angle and length of two vectors, we can determine the length of the cross product via the following equation. And note the right hand rule gives the direction of the cross product and angle. Like that. But if we know the components of the two vectors, we can compute the cross product via its definition, and that gives you the direction just based on its components alone. So if we have a definition of A is equal to components A1, A2, A3, and B is B1, B2, B3, then the cross product of A and B is the vector A cross B. So you'll go A2, so the way it works is A2, B3, and this is basically the determinant, and then the minus it by A3, B2, and then the next one is going to be A3, B1, like that. Yeah, so this is going to be A3, B1, then minus A1, A3, like that, and then the last one is going to be A1, B2, and A2, B1. All right, so it seems a bit out there, but yeah, that's A1. Yes, basically you have A cross B, A2, B3 minus A3, B2, and A3, B1 minus A1, B3, and A1, B2 minus A2, B1. And yeah, it seems a bit out there, but you can actually solve it or memorize it using the determinant form. So we could also use determinants and the standard basis vectors to solve the cross product. Just easier to memorize. So a determinant of order 2 is defined by, so if you have vectors A, B, and C, D, then what you'll have is that the determinant is going to be A times D minus B times C. That's what, hence the word cross comes in, the cross product, so you're crossing over. So A times D minus B times C. So for example, 2, 1, and the negative 6, 4, the determinant of order 2 is going to be 2 times 4 minus 1 times negative 6. That's 14. And a determinant of order 3 can be defined in terms of second order determinants as follows. So if you have three vectors a1, a2, a3, b1, b2, b3, and c1, c2, c3, then you can separate these up into three different second order determinants. The determinant of this one is going to be a1 times by b2, a1 times by determinant of b2, b3, c2, c3. So in other words, this times by, or this with this. And then the next one, then you're going to subtract. Notice to subtract, the next one's plus. You can get a2. This is just going to be an easy way to memorize the cross product. And then b1, c3. This one, it's the middle one cuts these in between. b1, c3, and then this is the b3, c1. Like that. So that's those ones you determined of those. In other words, b1 times c3 minus b3 times c1. And then the last one, this one here is going to be with this. So b1, b2, c1, c2, b1, c2, c2, c3, like that. And a good way to memorize this is if you have this, what you do is cross out this line and this line, you get this. And you do a determinant of that. And then for this one here, you would cross out this and this, you're going to get these. And then for the last one here, you cross out this and this, you're going to determine with that. So a3 times that, like that. And then, so then the cross product, it would use standard basis vectors. So these are just the, this one is, this is the 1, 0, 0 vector. It's the coordinates vectors. This one's going to be 0, 1, 0. And the k is going to be 0, 0, 1. So the vertical. The second one is the y, the other one is the x side. Anyways, so a cross b is equal to a, the same thing here, but instead of a1, you use I. And then j will use, instead of a2, we'll use j. Instead of a3, you use k. Just like that. And then you could write it all down. In view of the similarity between equations 5 and 6, we often write this right here. So a cross product is equal to I instead of a1, a2, a3. So we'll use this right here and then the other vectors there. Like this. And again, to get the cross product, you go determinant of this one right here. So you would cross this and this. Take determinant of this. Subtracted by the determinant of these, and then added to the determinant of this. Yeah. And you get this. And it's in vector form. So again, these would be the components for the x, components for the y, components for the z. Pretty epic stuff. All right, so question 9 states, how are the cross products useful? All right, so let's take a look at the solution. So solution, some useful properties of the cross product are listed below. 1, determining the perpendicular vector. So the cross product is perpendicular to both of its vectors, thus allowing to find the normal vector of surfaces and planes. So here's just a screenshot. So the vector A cross B is orthogonal to both A and B. It's a screenshot from my calculus book. And the second property that's useful is calculating the area of a parallelogram. So the area is equal to the length of A times by length of B times sine theta, which equals to A cross B, the length of that. So if you have a parallelogram like this, again, these are parallel, like that. So the vectors spanned by A and B, and then the sine of this one here is going to be the height of this. Like that, B, length of B times sine theta. And then if you multiply this by this, you're going to get the area on it. And then that's just the formula we have that I stated earlier. So A cross B, length of it is just equal to length of A times length of B times sine theta. So in other words, that's the cross product. And the length of the cross product. That's epic stuff. Yeah, so the length of the cross product, A cross B, is equal to the area of the parallelogram determined by A and B. And also, next setup is, similarly in 3D, calculating the volume of a parallelepiped. So the volume of a parallelepiped is equal to A area. So we know the area of the parallelogram times by H. So the height of this parallelogram. Of this parallelepiped. So basically take this height of this, area of this times by the height, and you're going to get the volume. So in other words, we're going to get the area of, if we have, this is B and C, these are B and C vectors, this area is going to be, this is going to be B cross C length, like that. That's this. And then times it by, this part right here. Yeah, this, if you have this vector right here, so then if you have the length of the vector, it's going to be like this. Put the opposite value sign around it, and then times it by the cosine. You're going to get that. So then this is a cosine A, cosine theta, like that. And the cross product right there, yeah, the cross product, and these are all lengths right there, but the cross product itself, B cross C, is a vector pointing up like this. And this actually it turns out to be just the same. Yeah, so if this is a vector, yeah, so then if you can consider the inside as a vector, yeah, which is a vector, so B cross C, and then you have the length of this vector A times cosine theta. This is just the dot product. This is the length of the dot product. So A dot B cross C, and you can recall the dot product. Let's go see what the dot product is. Where's the formula for the dot product? This right here, cosine, but I have it in the other formula here. Yeah, so the dot product is just equal to length A times length B times cosine theta. And in our case, we had the length of the B cross C, which is just a vector, so we could take the dot product of that. And we're taking absolute value to get the volume, because there's no direction, just a magnitude. And yeah, so that's pretty epic stuff there. Yeah, so A dot, and then this is the vector, right, like that, and take the length. So we're taking the length of the cosine, not just the cosine. So it doesn't have a direction, just has a size or magnitude. All right, and another useful property of cross product is calculating torque. So torque, or this sine tau, is equal to R across F. And the absolute value sign, the absolute value is, or the magnitude of the torque is equal to the magnitude of the cross product R cross F. In other words, it's going to be R, the magnitude of R times magnitude of the force times by sine theta. And this is what torque is. So the torque vector is going to be pointing this way. And if you have a force at an angle relative to the radius R from this spinning the torque axis, that's going to be like that. So the angle from that, and then you can apply this one here. So what it basically means is you're taking the sine component of this, sine theta, and then absolute value of F, or the length of F, and you're pushing it downwards like that. And so you're torquing this here, and the vector is there using the right hand rule. So if you have your fingers like this, it's just like drawing it messy, and your thumb like that, this is the right hand thumb, and yeah. But then you would put it over there, so this is the thumbs going this way. I mean, your fingers curling this way and your thumbs going outward. And that's the vector for the torque. So that's a useful thing. And it's used in angular momentum and so on, and a whole bunch of other uses, which is pretty cool stuff there. And also, there are many more applications in physics, geometry, and computer graphics. All right, continuing further. So question 10, how do you find the area of the parallelogram determined by A and B? And how do you find the volume of the parallelepiped determined by A, B, and C? Well, we already included this in the useful properties and so on. So we'll just repeat that again. So area of a parallelogram, solution to A is this right here is the length of the cross product of its two vectors. So the area of a parallelogram is equal to the length of A times by the length of B times sine theta, which is equals to the cross product, the length of the cross product. A cross B, like that, A and B. And the length of the cross product A cross B is equal to the area of the parallelogram determined by A and B. And then solution to B. And B states the volume of a parallelepiped is determined by the magnitude of the scalar triple product. Yeah, that's what you would call the scalar triple product, which you have the dot product and the cross product. So dot product gives a scalar, cross product gives a vector, but then you have vector dot product, you're going to get a scalar. And interesting, yes, they call it vector triple product. So there's the one we already covered. So V equal to area of the parallelogram times by height H, which equals to the length of the cross product B cross C times by length of A times the absolute value of cosine theta. And you get this scalar triple product. And it's going to be the absolute value or the length of the dot product with the cross product. Epic stuff there. And the volume of the parallelepiped determined by vectors B, A, B, and C is the magnitude of their scalar triple product. Again, screenshot from my calculus book. So V equals the length of the A dot B cross C. Epic stuff. All right, question 11. How do you find a vector perpendicular to a plane? All right, and the solution, we can find a vector perpendicular to a plane by taking the cross product of any two non-parallel vectors on the plane. Yeah, so in other words, all we need is, for example, if you have a point on the plane like here, P, X, Y, Z, so, and then this other point, P0, like that, all you need is another point on it, and then just take the cross product. So let's say you have P, let's say you had a Q like this. Q like that. So then all you need to do is first get the position vectors. If this is PO, this is going to be POQ, and this is going to be POP like that. And you just take the cross product of it, and you'll solve it. And here I made it neater because I think I'll leave these notes on there. And then this normal vector is just going to be the cross product of POP like that. Or instead of writing it like that, I'll just call this A and this vector B onto a point like that. Yeah, I think this is easier to do. So this point, let's say this point Q like that. So then this is just going to be A cross B vector. Yeah, so that's just easier and neater to do that. Yeah, and that's the perpendicular vector. And question 12 says, how do you find the angle between two intersecting planes? And let's take a look at the solution. So we could use the dot product of the normal or perpendicular vectors of the two planes. So recall the earlier formula right here. If theta is the angle between the non-zero vectors A and B, then cosine theta is equal to A dot B divided by the lengths of the A and the lengths of the B vector. So that's angle between two vectors. But in our case, if you have intersecting planes, so let's say if a plane like this intersects with one like this one across there at this angle theta, and then this angle theta is going to be exactly this one right here between the two normal vectors. So this normal vector going up, this one going down. You can think of this here as you flatten this, all normal vectors are going to be exactly in line. But then as you open it up, the angles open up exactly the same. And then basically this is then this is just calculate the angle between the two vectors using this dot product formula. So instead of A dot B, we use normal vector n1 dot n2 and then divide by the lengths n1 n2. This epic stuff. All right, going further. So question 13: write a vector equation, parametric equations, and symmetric equations for a line. So the solution is from earlier videos. Vector, parametric, and symmetric equations of a line are shown. So here's vector equation of a line. And so if you have right here a line, this line L, and it has a point on it, a vector pointing on this point PO, x0, y0, z0, and that's going to be r0 vector. And then you have just any vector on with this point here, p, x, y, z. And you have a direction vector v. This is a direction vector parallel to this line. Like that. Then the vector equation of a line is equal to this point here. This is the vector with a point anywhere on it. Is equal to r naught vector plus a parameter t times by direction vector v. And I believe this a vector is just this t times v like that. And this is just stating that this is just basically a multiple of this. So you're just scalar multiplying this v such that this is going to be equal to t times the vector. So this is direction, and then you scale it up. So for example, at this here, we're going to have a large t. So this v is going to be extended out like that. So v vector like that, giving a direction, and then this is going to be t times v, etc. Anyways, so I'm just a bit messy here. Again, it's just a concept check review in case you've seen all the other videos. So make sure to watch those, and this is just a review of everything we covered. So parametric equations of a line. And to get the parametric equations, well, we would do the same thing with the starting the vector equation of a line. R equals r naught plus t parameter times v direction vector. And then what we would do is, well, this point right here. So this is a point on it. This is going to be x, y, z components. That's just r. It's just going to be x, y, z like that. But then you could separate these up into its components. So it's going to be x naught. Plus, it's just going to be this right here, x naught, y naught, z naught, plus t times, and then this is the direction vector, and the direction vector has a, b, c components, and then times by parameter t. And then you can add up each component, so x naught plus ta, y naught plus tb, and z naught plus tc, and then separate these all into separate equations. So you'll have the x component is equal to x naught plus at, then the y is equal to y naught plus bt, z equals z naught plus ct, and these are the parametric equations of a line. Epic stuff. And then lastly, the symmetric equations, again, starting with the vector equation r equals r naught plus tv. And the direction numbers are these. This is just direction numbers giving you the direction of the line. So v vector is equal to components has vectors a, b, and c. And then the symmetric equations is, well, we take these parametric equations, and then we just make t equal for all of them, just separate for t, and then equate them all. So in other words, move this here, so x minus x naught, and then divide this by a equals to t. Equals to t, like that. And similarly, y, so move the y over, you're going to get y minus minus y naught divided by b is equal to t. And then similarly for z, z minus z naught divided by c is equal to t. And then t's all equate, so you get the symmetric equations of a line right here. So that's epic stuff there. All right, let's continue further. Question 14. This states, write a vector equation and a scalar equation for a plane. So not a line, a plane. All right, so let's look at the solution. So the vector and scalar equations of a plane are shown. So a vector equation of a plane, so you can write it like this. The vector one is just going to be the this normal vector dot. Then you have this this vector on the plane r minus r naught with that position vector. And then the dot product of it is equal to 0. In other words, it's perpendicular to this point, to this vector connecting from this point to this point, and it's perpendicular, so hence the dot product is equal to 0. So then you could just write it like this. And you can also separate this up, so r, you can also write this as r dot minus n vector times dot r naught, and then move this over to the other side. This is the negative. So you could also write it like this. N dot r equals to n dot r naught. So you can write it like that. Just epic stuff there. So dot product with this vector and this. And again, it stems from the dot product of this and this are perpendicular, hence dot product is 0. And the scalar equations, the scalar equation is actually taking the dot product. So remember, this n is equal to a, b, c. So then, so the dot product is going to be a times it by, the next one is going to be r minus r naught for the x component. That's just going to be x minus x naught. Then the dot product is so a times x minus x naught. The next one is going to be b times it by the y components. Oops. Yeah, so the y components like that. So then b times y minus y naught. Last one is z over the c times it by z minus z naught. And they all equal to 0. Dot product is equal to 0. So yes, that's quite amazing stuff there. All right, let's go further. Question 15. And question 15 states, how do you tell if two vectors are parallel? And B states, so that's part A. Part B states, how do you tell if two vectors are perpendicular? R. And then C says, how do you tell if two planes are parallel? So if two vectors, the solution to A, two vectors are parallel, then the angle between them is 0. Yeah, so if two vectors are parallel, so you have a vector like this and this one, if you superimpose them, the angle between them is just going to be superimposed, going to be 0. Theta is equal to 0, like that. And then we could take the cross product. So if two vectors are parallel, then the angle between them is 0. Thus the cross product is 0, since sine theta, sine 0 degrees is equal to 0. So recall that the cross product, if theta's angle between A and B, so where theta is between 0 and pi, then the length of the cross product is equal to length of A times length of B times sine theta. And remember, sine looks like this, and it's at 0 is equal to 0 for sine theta. And two non-zero vectors A and B are parallel if and only if basically this cross product is equal to 0. Yeah, so if this is 0, the length of the cross product is 0, and if it's 0, it just also has a 0 direction, which is just 0. So the cross product has to be 0 for parallel vectors. So if you have a parallel vector like this, cross product is going to be 0. It's not going to actually have a direction. It's just going to have 0 direction. You can call it that. All right, so now let's go look at the solution to B, and this one is asking, how do you tell if two vectors are perpendicular? And, so if two vectors are perpendicular, then their dot product is 0, as we covered earlier. So since, again, cosine 90 degrees is equal to 0. So if theta is the angle between the non-zero vectors a and b, then cosine theta is equal to a dot b divided by the lengths a and a times b there, divided by those. And two vectors a and b are orthogonal if and only if the dot product is equal to 0. Again, this means 90 degrees. Cosine 90 degrees or pi over 2 radians is equal to 0. And hence it's used in a definition for the plane. So solution to C, and the C is we're asked, how do you tell if two planes are parallel? That's interesting. And this was again from my earlier video. All this is from earlier videos. So if two planes are parallel, then the angle of their intersection between their normal vectors is 0, which can be determined using the dot product. So again, this is another play on the dot product. So if you have two planes that are parallel, if this angle is equal to 0, you're going to have the planes like this. They're not going to be intersecting. They're just going to be flat out 0. And and if the angle is not 0, then they are not parallel. Yeah, so if it's not 0, eventually you can you will cross the plane. So if you're like this, if it's not 0, eventually it will cross it because these all extend out to infinity, and so on. Let's cross it. And yeah, so that's parallel lines. And again, using the formula just for the dot product formula over here with cosine, but instead of that, use the normal vectors n1 and n2. So cosine theta is equal to n1 dot n2 divided by lengths n1 and n2. And now let's look at question 16. So this one we're asked, describe a method for determining whether 3 points P, Q, and R lie on the same plane or same line. Then part B says, describe a method of determining whether 4 points P, Q, R, and S lie in the same plane. So here, describe a method of determining 3 points. Let's look at solution to A. To determine whether 3 points lie on the same line, we could take the cross product of the position vectors PQ and PR. So in this case, we have PQ and R. If you take the cross product of them, if the cross product is 0, then the position vectors are parallel, hence the points PQ and R lie on the same line. Here's the notes from our the earlier ones I screenshotted. So if the angle theta between A and B, if theta is the angle between A and B, where theta is between pi and 0, then the length of cross product A cross B is equal to length A times length B times sine theta. And using the right-hand rule for the direction, this is going to be perpendicular to these right here. But if it's 0, if these are parallel. So if B is on this, it's going to be 0, or the 0 vector. You could go 0 vector like that. So the magnitude is 0, has no direction. Right-hand rule gives a direction of A cross B. So for example, to illustrate this, I will draw this out. So let's say we have like this. This is going to be our Z. And let's say we had, that's our Z, this is our Y. And I'll fix this up a bit. This is going to be our Y. And this is going to be our X axis like that. This is the origin. So let's say we had a point here, P, like that. And let's say we had a point Q. So we'll draw it on one line to illustrate. So this is Q, this is R. So then this length right here, this is position vector PQ. I'll put it on top, actually. Actually, I'll put it on below. Yeah, that was good there. And let's say this is PQ, like that. And the next one, I'm going to draw this in red. And let's draw this in red. Okay. So let's say we had now from P like that. Here, actually, just move this over so it's actually in line. So we have from here to here. This is PR. Like that. So if it's parallel, so from there to there, if it's parallel, then the cross product, the angle is 0. Yeah, so then the cross product would be perpendicular, right? Except it would be 0. So we'll have PQ cross PR. PR is equal to 0 because the angle is 0. This equals to the 0 vector. Yeah, so that's going to be 0. So the angle is actually 0. So you're just going to have like this and this. PQ, PR, like that. Yeah, so the angles is 0 between them. So in other words, they're parallel. so this is going to be 0. If it's so if cross product is 0, then the position vectors are parallel. Hence, the points P, Q, and R are on the same line. Yeah, so they're all exactly on the same line, like this. Whoops, like this. So they're all on the same line. So yes, I'll just erase that. So epic stuff. All right, and now let's take a look at the solution to B. And B was asking, describe a method for determining whether 4 points P, Q, and R and S lie in the same plane. So same plane. So let's go here. So it's a determine solution to B to determine whether 4 points, whether 4 points lie in the same plane. We can compute the triple product of the position vectors PQ, PR, and PS. Or compute the scalar triple product of the position vectors PQ, PR, and PS. In other words, if the triple product is 0, the scalar triple product is 0, then the volume of the parallelepiped is 0, thus all the points are on the same plane. So in other words, so we have this, recall the volume of this parallelepiped is equal to the volume of this parallelogram times by the height h. And the volume of the parallelepiped determined by the vectors A, B, and C is the magnitude of their scalar triple product. So V is equal to A dot, the length of the absolute value of the A dot of B cross C. Yeah, so that's what we have there. And if all these points are on the same thing, so if you have this vector here was actually here, the height would be 0. So h is 0. So the volume is going to be 0. So instead of that, if you have it there, it becomes 0. And I'll just illustrate that right here. Yeah, so let's say we had 4 points P. Let's say we had Q here. Say we had R here. Let's say we had S here. So if we're doing the scalar triple product, if all of these are on it, like that. So if we have this, let's say let's call this A, let's call this B, let's call this C. Yeah, and let's say that if they're all on the exact same plane, the volume here is going to be 0. So V is equal to 0. So in other words, they're all on the same plane. All these are on the same plane. They have no thickness to this this parallelepiped. No, it just becomes a parallelogram if these are all on the same plane. All right, and now let's take a look at question 17. And this one's going to be a bit more in depth, and this is going to be on distances between points, lines, and planes. In part A says, how do you find a distance from a point to a line? Part B says, how do you find a distance from a point to a plane? And part C says, how do you find a distance between two lines? So let's take a look at the solution to A, which is the distance from a point to a line. So to determine the distance from a point to a line, we could use the fact that the magnitude of the cross product is the area of a parallelogram, where the height is the distance from a point to the base, which is just a line. And in my earlier videos, I didn't actually use this method. I used a different one using planes and so on. But this one's, I think, I saw it online. It's and I really like this one. This one's much easier to grasp and calculate and so on. And also has to visualize as well. So recall from my earlier videos, so the cross product, if you have A and B, so A cross B, the magnitude of it is going to be the area of the parallelogram spanned by A and B. And the area is just going to be, well, the length of this times by times it by the height, which is going to be the length times sine theta of this one there, which is again just a rectangle. If you shift this over like this is just going to be a rectangle where this is A and the height is h there, like that. So just the height of the rectangle. All right, so now let's go ahead and see how we go about solving this. So let's say we had, and just for completeness, I'll draw the xy axis like this. So this is going to be the y, this is going to be the z, this is going to be, this is going to be the x, this is going to be the z, like that. And let's say we had a line, and I'll draw the line like this. So we had a line L, like this. This is going to be our line L, and let's say there's a point on it that's going to be, let's say that's our starting point Q. So point Q, like that. And the initial vectors are not vector. And then we have any vector on it, R not, just R vector. And this is the equation of the line is going to equal to R vector plus a parameter t times by the direction vector v. So let's draw the direction vector along this line like that. So it's our v, like that. And let's say there's a point P right here, and we want to know the distance from this point to this line. So this is going to be point P. And again, we use the area of the parallelogram. So we'll take this vector like that. So the vector PQ like that. And I'll just put this is going to be the length of this vector PQ like that vector. And I'll just leave it like that, PQ vector like that. And here I'll just change the direction just so it's consistent. So PQ from P to Q. It doesn't matter which one because we're taking absolute values and distances and so on. So what we'll do now is, so we have that. And then the area of the parallelogram is going to be, well, we'll just parallelogram it all the way across there. And then this one's going to be across there. So then this area like that, this is the area. Area is equal to the absolute, this is going to be PQ like that, cross, and then V. So this is our B, and then the direction vector is the V. And the height is going to be this this absolute value sine, or the length of the B, which is this one sine theta, and that's going to be, well, this height. We could from here all the way down here, or we could just draw it from here to here. So that's our distance D equals to, this is going to be the distance like this, P, Q, that's our B, sine theta, like that. And the area is equal to this one as per that equation in my earlier videos. So that means we can solve for this distance D. So we'll go like this, area equals to PQ vector cross with V vector, and this equals 2 V vector times by the distance. It's going to be PQ, PQ sine theta. Put it like this just because this is going to be our distance D. D, like that. So that's our distance. And you can view it as basically this component projected onto this over here. All right, and then rearrange that so we get distance is equal to this PQ sine theta, which equals to, I'll just put it for completeness, this is going to be, this is the vector, the length of the vector PQ onto sine theta, but we don't know what theta is, so we'll just put it there, but we know these other terms, so then this divided by over to there, so we're going to get PQ vector cross with V divided by V distance, like that. So the cross product along there. So yes, this is epic stuff there. All right, here, and I'll just cross, I'll just bold this. So that's the distance right there. All right, going further, note that in 2D, so this is 3 dimensions, but then if it was in 2 dimensions, well, it's going to be exactly the same thing here, but so we could use this formula right here. This will simplify it to this anyways, right here, because you can see the distance right there, or that direction vector there. This is a B term, the other one would have a C term in 3D, but if it's 0 for the Z, you're going to end up something like this. So yeah, you could use this formula. So if the distance from x naught, y naught, and from this to this line, and then this is going to be this formula over here, distance equal to absolute value of a, where again a defines this line, ax plus by plus c equals 0. So ax naught plus by naught plus c divided by square root a squared plus b squared. And where the a and b, they govern the slope of this line. Yeah, so that's pretty epic equation, so make sure to watch that video. All right, let's go further. So solution to B, and this one was asking the distance from a point to a plane. All right, so the distance from a point to a plane can be calculated by the equation below. This was my earlier video. So distance from a point to a plane, you could just use this formula. So you have a point like that, and then this is from this, you have this P naught and P1, it forms this B vector. And you have this n vector is the perpendicular one. The distance is going to be the full length here. So this n vector could be small, it could be big. You don't know what it is. But you can solve this from just any vector, any 2 vectors all along. Any 2 vectors along this plane, and then take the cross product. And then D is the component of B projected onto n, which is going to be the n dot B divided by the n like that, or the length of this n vector, like that. So that's this one, and there's a formula for the distance from a point to a plane. And again, note the similarities with this distance. With this one, distance to a point to a line in 2D, it's exactly basically the same thing. And I also note another similarity. This one is the n, the normal vector of this plane, dot b. And then compared with this one, where we use a parallelogram, we used a cross product, but we had the direction vector, not the normal vector. So this is right here, direction vector cross b, or pq. And then using the plane one, we could do dot product with the b and the normal vector. So it's interesting. Anyway, so we could use that formula, and let's go further and now solve the solution to C, which was asking the distance between two lines. So if two lines intersect, then the shortest distance is 0 at the point of intersection, and we can equate both lines and solve for their parameters. So if we have the simple case where they actually intersect, so let's say you had a line like this, we'll call this L1, and this one's L2. Like that, and yes, that's L2, and so there's a point of intersection, so we can just equate them like that. So let's say we have L1 is equal to R. The equation for L1 is equal to, we'll call this R2 equals to like that. Yeah, R2. Actually, instead of R naught, I was call this P2. Let's say it's a point on it or vector of it to it. So P2. This is actually P1. 1 vector plus we'll call this t, and then we'll have the direction vector 1. Then this one here, this formula would be R2 equals to P2 vector plus S parameter V2 vector. And this one again, the direction vector is V2 is like that. And let's say it has a point on it. The starting point is going to be our P2 like this one. So that's our P2. This is point P1 on it, and then the vector is just going from the origin to this. That'll be P2 like that. I'll just draw it for completeness. So again, if you have our x, y, this is going to be a y, z, x like that. This is going to be our P2 vector. Or this is just our P2. There's a point. And the vector P2 with an arrow on top. All right, so we have that. And this direction vector is going downwards. This is our V1, like that vector. And this is the point of intersection. And then this one, we just equate them and then solve for S and T such that all these are equal. We have the exact same point. So you set those equal to it. So we go R1 vector equals to R2 vector. Solve for solve for T and S, and then once we do that, we plug that in, and then so if we can solve it, the distance is 0. Yeah. So going further, so if there's no solution, then the lines don't intersect. So then they're not they don't intersect. So we got to go further. So if two lines are parallel, then the cross product of their position vectors is 0, and we can solve the distance by the same method as with the distance between a point and a line. Yeah, so what this means is basically, if two lines are parallel, their cross product is of their position vector 0 because they'll be both parallel. Like so, if we go back to over here, so what I'll do is let's say we have two parallel vectors. I mean two parallel lines. Let's call this line line 1. It's going to be line 2. So this is parallel. So their direction vectors, we'll call this V1 and V2, like that. So if you were to take the cross product of them, you're basically going to have a V1 like this, V1, and the other one's going to be overlaid on top of it. V2, cross product is going to be 0. V1 cross V2 equals 0. Because... also because the sine theta is 0. Yeah, so sine of 0 would be 0, like here. Yeah, so sine of the angle 0, so that as 0 angle like that is equals to 0. And that's because the cross product, the magnitude is equal to the area of the parallelogram, which has that sign in there. And here I just wrote this right here as well. So if two lines are parallel, then the cross product of their position vectors is 0 because sine of 0 degrees is 0. Yeah, so then we can basically, so basically we can just draw this out as parallel, and that means is, well, if we had a point like here, I'll call this P1, and let's say we had a point P2, this vector here is the P1, P2 vector, like that. So then again, area of the parallelogram, if this is V2, I'll draw this a bit. Actually, we can, it doesn't matter where you draw it, so I'll keep it at V2 like here. So the area of the parallelogram is going to be like this all the way across here. So there's our area. So this is our area. Area is equal to, yeah, let's put it here. Area equal to P1 cross, yeah, this is P1, P2. Actually, I'll write this out later. So we have the area there. This is our area. And then this height is going to be the distance across it. So I'll just draw it like this. So this is going to be our D, is our distance. And that distance is just going to be the projection of P1. This is just going to be P1, P2, P1, P2, like that. And then times by sine theta. This is going to be like that, sine theta. So in other words, this is the same distance across there. Sine theta. Like that. And again, that's because this is going to be perpendicular, like that. All right, so that's perpendicular. That's the area. So in other words, we're going to get area is equal to, yeah, it's going to be the P1, P2 vector, yeah, cross product with, and we're doing its magnitude of the cross product with the direction vector V2. And it's going to be the area of the parallelogram. And so this cross product is going to equal to, we'll put this V2 in front so that we could put this P1, the length of them, P1, P2, line like that, and then it's going to be their sine theta. And this is again as our distance, so we could rearrange it. So distance, yeah, distance is going to equal to, yeah, distance is going to, and then move this over. So again, the exact same thing as before. So we have that. And I'll keep writing it just for completeness, so we can drive the point home how to solve for distances between points and lines. And it's going to be like that. And again, this equals to, just for completeness, I'll bold this. This also equals to P1, P2 sine theta. But we don't know sine theta. Yeah, we don't know what the angle is theta there. Yeah, but we could solve for it. Obviously, we could solve for it. We know this point, we could solve for this. But then we also need to know the direction vector. So direction vector matters. So once we solve this, then we could throw that inside and solve for theta. All right, now going further. So if two lines don't intersect and are not parallel, then they are skew lines. So that's the only other alternative we have. And skew lines can be viewed as being on two parallel planes. Again, regardless of what the skew lines are, this is going to be on two parallel planes. And here's a link to GeoGebra from my earlier video. And so here is a pair of skew lines. So it doesn't matter where you draw the line in here. I'm just going to hide the plane right here. So let's say we had, and also hide this direction vector. So let's say you had any line like here, and that doesn't intersect. So that doesn't intersect. That means there's going to be a gap that it never touches. And again, it doesn't matter what the skew lines are, what the formulas are. If there's somewhere else, let's say it looks like this one here. Basically, all skew lines could be viewed the same just by rearranging the axis. So again, so you can move it around like here, but then they can all be formed by parallel lines because they never touch. So you can always form a set of parallel planes. Parallel planes like that. So we can draw two parallel planes across it. So there's the line, the blue one, there's the black one, and they're on it. Doesn't matter what it is, you could always get it. So if it's somewhere over here, the lines, you can just rotate it. I'm just showing you how that's always going to be parallel. You're always going to have two parallel planes making the lines. So if we have two parallel planes, this means we could just use a distance between a point and a plane formula. Use a distance between a point and plane formula by first obtaining the normal vector of the two direction vectors. Because once we have the normal vector, we basically have the equation of the planes for either of them. Yeah, so this means, as I went over in my earlier video on distance between skew lines, all you need to do is find a point on one of the lines, and then the distance would be to the plane that contains the other line. So in other words, the direction vectors included in that cross product to obtain the direction vector. Yeah, so basically if you have a point like here to this plane that contains a blue line there, it's the same thing as this, containing this blue line, blue plane right here. But this one would be the actual line there. So this point, and this would be on it like that. Or actually this could be, but again, it's just skew, so it could be a different direction, but it's not parallel like that. It just means we can't use a cross product. We could use the dot product. And then once we get the equation of the plane of one of them and the point on the other one, and then we could just use the basic distance from a point to a plane formula, which is D right here equals the component of B, vector connecting 2 points on the plane, 2 points on the lines, and then onto the normal vector of either plane, like that. Because they're both going to have the same normal vector because they're both parallel planes. And we'd use a dot product n dot b divided by n, like that. And note that the distance formula is just a scalar projection of a vector connecting the two lines onto the normal vector. And again, the normal vector we can determine from the cross product of the two direction vectors. And and I'll put this right here via the cross product. All right. So, and then the distance we'll use a dot product. So just to illustrate all this, let's just draw this out to make it more sense. So let's say you had it's going to be two parallel planes. So it's like this. These are the skew lines. So we have a plane like this. And let's say we had a line L like here. So this is going to be our line L1. And it's going to be on P1. So P1 plane and line L1 like that. And then we had, let's say, our second plane and it's parallel like this, and let's say it goes something like this. So it's skew, and it's going to be our L2, and this is going to be our P2 plane, like that. All right, so we have that, and let's say we had a point P. I'll call this P1. Actually, this is plane 1. I'll call this. I'll call this plane 1, just so it's plane 1, just because we're not going to use that plane there. Plane 2, we're not going to actually be using that term there. So this is going to be P1 point like this. And let's say you had a point on here, P2. Like this is on line 2. We have let's actually move this around here. Let's go P1, and this is going to be on it like that. And let's draw a line connecting it. I'll draw this actually in maybe use a different color, red. So I'll draw it in red. And so we go from P1 to P2. This is going to be our, I'll call this P1, P2 vector, like that. So then the distance is going to be from here. It's going to be the along the normal vector. So this is going to be right angles like that. And it's going to be right angles as well from this to that. So this is going to be our distance D, like that. But it also has a normal vector. I'll draw this in black. The normal vector, it goes like this. Oops. So normal vector is going to be from here. It's going to be like this. This is going to be our normal vector and vector. And this equals to we need the two direction vectors. So this direction vector is going to be V1 of the line. And this one is going to be V2. So this is just going to be, the normal vector is just going to be, actually, this is D. I'll try this in black like that. And same with this one here. I just drew the line there just so it's different from this plane there. So P1, P2 like that. And this is going to be V1 cross product V2. And you can see that you can stack them on top of each other because we're looking at along this direction of the normal vector. And you can see that visually. You just put the V1, let's just stack them on top. If this is the V2 like this, and then V1's across there. Normal vectors is going to be, this is the normal vector. It's just going to be right angles from of both of these lines. That's going to be a cross product, like that. And then, the distance is just going to be the scalar projection of this P1, P2 along the D, right there, along the normal vector. So that's the distance. So distance is going to be equal to, this is going to be, I'll write that in that, the vector, scalar vector format. So component of, is going to component along the normal vector n of the P1, P2 like this. This equals to, it's going to be the projection of it. So the projection of this onto this, and that's just going to be using the formula. Again, this is just going to be P1, P2 dot product, the absolute value sign of it, of the normal vector divided by the normal vector. So the unit vector, this one here multiplied by the dot product, it can be viewed as multiplication of the unit vector there. This is distance. Somewhere, yeah. And then this is just the formula for distance between a point and a line right here. This is the B. I just called it P1, P2, the vector, and this is the n dot B. It doesn't matter if you have n dot b, or this also equals to b dot n. Like that. So it doesn't matter which direction you use it at. So n dot b, then divided by the n, like that, and then you get this formula, and so on. So I will just bold this right here. So that's our distance right there. Yeah, and that's the distance between two skew lines, just using parallel planes and so on to get solved up. And watch my earlier video on this one as well. Again, this will be in the sections playlist. All right, continuing further to question 18. What are the traces of a surface? How do you find them? And yeah, this one's going to be just reading out stuff. So solution: traces are the curves of intersection of a surface with planes parallel to the coordinate planes. And yeah, and we can find traces by setting the x, y, or z coordinate to be to a constant k. For example, an ellipsoid is a surface with vertical and horizontal traces being ellipses. So these are curves of intersection. Let's simplify this right here. So here's an ellipse right here. So the traces, there's the vertical traces right here. They are the curves of intersection with planes parallel to the coordinate plane. So this one is going to be, this plane right here is parallel to the z one right here. So this is going to be parallel to the z, this one, and then likewise you also have the horizontal one. So horizontal right here is parallel to the y one like this, and also the x one, I believe. Yeah, and then you also have, you could all below it right here. So all the traces, wherever you slice it off, any plane you cut through that's parallel to the z, x, or y, you're going to get a ellipse. So that's why this shape is called an ellipsoid. Here's a formula for it, and you obtain it by setting the x, y, or z coordinate to a constant k, and then solve for that 2D trace. So for example, so if this is a formula right here. So if I set z equals to k, and here I just quickly updated this. I had the z one here twice. So what we'll do is basically in this case, the first one is we set this one here, set z equals to k. So set z equals to k here, and then move it over to the other side because you're just going to get a constant. You're going to get a 1 minus k squared over 4. And then you're going to get the equation of an ellipse right here, as long as this one here is, this k squared is less than 4. Yeah, so that the right side is going to be positive, and this will fit in ellipse right there. Yeah, because this one here is going to be positive, so you can't have a negative here. So you're going to not have a solution for k that's, for k is going to be greater than negative 2. It's going to be less than negative 2 or greater than 2, the absolute value of it, greater than 2. And yeah, so this ellipse right here, you could tell it because it's x squared plus y squared divided by 9, where this one right here is not the same as this one here. The divisor on this, or the denominator of x squared is 1. If it's equal to 9, if it's equal to this one, then you're going to have a circle. And if this is equal to 1, or in other words, k is equal to 0. So here's just recall equations of parabolas, ellipses, and hyperbolas. So a circle would have something like this: x squared plus y squared equals a squared. Or you divide by a squared so that this equals to 1, and you're dividing both of these by a squared. An ellipse is just where the divisor right here, a squared, is not equal to b squared. So you're going to have, it looks like that. And this equals to 1. And then the parabola, here's the parabola like that, and there's the hyperbola equation there. And so you could use these basic traces and so on, those formulas to determine what kind of traces these are. So this was a horizontal one. That's z equals to k. So you go z equals to k, for example, let's say z equals to 1. Equals 1. So then you would draw a plane across at this point, and then you're going to have a horizontal ellipse at this, around that point there. So horizontal around z equals 1. And then these are the vertical ones. So if you have x equals to k, so set x equals to k, and then so you set it equal and then solve for it. So if x equals to k right here, then you would move this over to this side. So you're going to have 1 minus k squared, and you're going to have this. This is also an ellipse. Y squared over 9 squared plus z squared equals 4. And again, this can't be, this right side can't be 0, so then k is going to be between -1 and 1. So you can't have 1 subtracted by a bigger number. And yeah, what we get is, in this case, it's going to be a vertical ellipse, basically, because we're setting x equals to Yeah, so we're going to go x equals to a number. Let's say we have x equals to 0.5. So we're going to have to draw a plane like this. It's going to be all of these are going to have where this is at x equals to, let's say 0.5. You're going to get a vertical ellipse. So a vertical plane that cuts through this all, and then all these points are going to be an ellipse. Is going to be shaped like this. Yeah, so that's going to be, think of it like that. So you're cutting through at the x equals 0.5 plane, where any point on this, the y and z are going to be different, but the x is going to be equals to 0.5. And it's going to be a vertical trace, like a vertical ellipse. And similarly, when we set y equals to k, so y equals to k, move this over, you're going to get, right here, you're going to get x squared plus z squared equals, divided by 4 equals 1 minus k squared over 9. And then where this k has got to be less than 3 and greater than -3, like that. So that this is going to be greater than 0, this is going to be greater than 0, and this is also going to be greater than 0, like that. Yeah, so that you get an ellipse and so on. And just a note, if it was equal to 0, if this whole thing equals to 1, so if you set them equal to 3, this would be 0. But then you're going to get a 0. This has to be a 0 and a 0, but 0 is not on there. It's going to be in the center there, and you can't actually have that. If you plug in 0 into all of these, you're going to get a actually it will work. It'll just be a trivial one. So if this was 0, this is 0. This would be 3. So you're going to get a 1 equals to 1, like that. Yeah. So that would still work. So you can have it still there, but it won't be an ellipse though. You're just going to get it at this point here. So y is 3. Yeah, you're going to have 0, 3, 0. So yes, that is would be the point there on it, or plus or minus. So you can also have a -3 as well. So yes, that works, but it won't be an ellipse. So hence between these you're going to get the ellipse, and beyond that you won't have a solution. All right. So and then again, that's at y equals. So for example, if you have y equals to 2, for example, and yeah, that's y equals 2. It already has a trace for us. You can have a vertical plane like that, and then this is cut there, and this is at y equals to 2. Y equals 2 plane. You get a vertical trace like that. It's just epic stuff there. All right, so now let's continue further and now look at question 19. This one states, write equations in standard form of the 6 types of quadric surfaces. And let's just dive right into this. So solution, the equations in standard form of the 6 types of quadric surfaces are listed below. So you have the ellipsoid right here. So we have this, to set up this equation, notice it's the x squared plus y squared plus z squared, all of them on the left side of the equation, then you have equals to 1. All the traces are ellipses, and if a, b, and c are equal, then the ellipsoid is a sphere. It's like that. And the cone, so you have a cone like here, this is, instead of this right here, this would be on the other side, and you'll get rid of the 1. So that's the difference between there, and you get this cone like that. And horizontal traces are ellipses. If you cut them horizontally, like that, you're going to get ellipses and so on. And vertical ones, vertical traces in the planes x equals to k and y equals to k are hyperbolas if k is not equal to 0, but are pairs of lines if k equals 0. If k equals 0, you get a line like that and this. Otherwise, the vertical traces will be these hyperbolas. So that's a cone. And then you also have the elliptic paraboloid right here. This one here is similar to this one, except instead of the squared, you get rid of this power there. Yeah, so then this is one of the ones, the vertical one has a power of 1. So horizontal traces are ellipses, vertical traces are parabolas. As elliptic paraboloid, so you have this is ellipse this way, then you have parabolas going up vertical. And the variable raised to the first power indicates the axis of the paraboloid. So this is the x one, the z1 is this one. If it was the x, it would be opening up this way. And if it's the y opens up that way, the x would be open up this way. Yeah, so yes, epic stuff there. Oops. Like that. All right, just erase this. And the next one is hyperboloid of one sheet. So you'll have all these right here, x squared. It looks like the ellipse, but then this would be a negative sign. So instead of the plus, if it's a negative, instead of the ellipse like that, if you have a negative, it becomes hyperboloid of one sheet. It's like an inverted ellipse there. That'd be cool. And then horizontal traces are ellipses. Vertical traces are hyperbolas. You can see this up and down. And the axis of symmetry corresponds to the variable whose coefficient is negative. So this one would be opening up like that. So that's the tube in there. Looks like a power plant. All right, so the hyperbolic paraboloid. So this one's an interesting one. It looks like, so it's a parabola like this, but then on the horizontal side, it is actually the hyperbolas. So if you draw a plane like this, you can have hyperbolas this way and this way. And the other one. So this is similar to this one here, similar to elliptic paraboloids that over c power of 1. But instead of this plus, we have a negative. So we have a negative there. Then horizontal traces are hyperbolas. Vertical traces are parabolas. All the vertical ones is it only goes up once like that. All the vertical traces are like that. Yeah, so horizontal are parabolas, vertical are horizontal are hyperbolas, vertical are parabolas. They all go up like that, and etc. Or downwards, depending on where the actually this one's going up like that. I think that they all go up like that, and then a vertical on this side. You also have a actually this one's going down like that. This one's going up, and then these ones going down. If you cut it like this, this goes down. Then if you cut it this way, these ones go up. Interesting. And the case where c is less than 0 is illustrated. Yeah, this is c is less than 0. If it was greater, I think it would be inverted. Or, yeah, I think it would be inverted. Anyways, going further, there's a hyperboloid of 2 sheets. If you go back to the hyperboloid of 1 sheet, like it's like this, you have a negative there. And then you have 2 plus. But then I think it's the other way around. You get negative, negative, and then this becomes a plus. Like that. Yeah, so this one's negative, negative, and then this is plus. So horizontal traces in z equals to k are ellipses. If you do a z equals to k, you get an ellipse like that. Are ellipses if k is greater than 0 or k is less than k is greater than c or k is less than c. And vertical traces are hyperbolas. So vertical, cut them like this, you're gonna get a this and a this. And the 2 minus signs indicate 2 sheets. Yes, interesting. So there's 2 sheets like that. And summary, here's a summary of all of them. So there's ellipsoid, elliptic paraboloid. This is the, the hyperbolic paraboloid. You got the cone, hyperboloid of 1 sheet, hyperboloid of 2 sheet. And yeah, that is all for today. Hopefully you enjoyed from this epic review of it. And very interesting stuff. It was pretty much a review of everything, but I did include some new stuff, such as the finding the line distance from a line to a point using the parallelogram method. I like that method better than finding the plane and so on. So that's interesting. So you could use this setup and find the equation distance from a point to a line, or between 2 lines and so on. Anyways, that is all for today. Like always, you can download these exact notes in the link in the description below, as well as viewing these in sections playlists. I'll try to make. I'll do definitely for those equations of distance between lines and planes and points and so on. But I may make it for others, but we'll see, depending on what I think is best to shorten and so on. Anyways, that's all for today. Thanks for watching, and like always, you can download these exact notes and link in the description below, as well as viewing it notes on the Hive blockchain and article format. Anyways, thanks for watching. Stay tuned for another Math Easy solution.